Okay, so let's do one example for gas mixture. In this problem, we have a mixture that includes 2 kilogram of oxygen, 3 kilogram of nitrogen, 7 kilogram of propane, and the question is asking for the mass fraction of each component in part A. So mass fraction is basically the ratio of mass of each component to the total mass. So the total mass or the mixture mass is simply sum of the mass of each component. So we have 2 kilogram of oxygen and 3 kilogram of nitrogen and 7 kilogram of propane. So we have a total of 12 kilogram of gases. All right. So let's say if this is our tank, in this tank we have oxygen. So let's say that these dots they show oxygen molecules. We also have nitrogen in this tank. So the red dots are nitrogen. Maybe I should do them more distinct, but these are nitrogen. And also we have propane. So for propane, maybe I can use another color. So I'm showing that with cross. So let's say these cross are propane molecules, for instance. Okay, so this is what we have in this tank. Now, the mass of total components or mass of mixture is 12 kilogram. But this is not we are asked for in part A. In part A, we want to find the mass fraction of each component. So mass fraction of oxygen is basically equal to mass of oxygen over mass of the mixture. So oxygen mass is 2 kilogram and mass of mixture is 12 kilogram. So that mass fraction is 0.166. And it's a dimensionless number because this is mass divided by mass. So there is no unit for that. Likewise, mass fraction of nitrogen is equal to mass of nitrogen over mass of mixture. Okay, and that will be 3 kilogram over 12 kilogram, which is 0.25. And finally, mass fraction of the propane gas is mass of propane over mass of mixture, which is 7 kilogram over 12 kilogram, which is equal to 0.583. Now, if you notice, the sum of these three mass fraction is equal to 1, and this is exactly what we had in the lecture. Sum of MFI is equal to 1. In this particular case, I starts from 1 to 3 because we have 3 components here. So if you just add these 3 numbers up, you will get 1. So these answers, by the way, these numbers are answers in part A. So these are the answers in part A. In part B, the question is asking for the mole fraction of each component. Now, mole fraction is pretty much the same concept, but instead of the ratio of mass, it is the ratio of the number of moles. Okay, so if that was part A, in part B, we want to find what is the ratio of, let's say, the number of moles in oxygen to the total number of moles. Okay, for instance, NO2 and N or capital N being the number of moles is equal. What I'm going to do basically, let me clarify what I'm going to do. First of all, I'm going to obtain the number of moles that we have for each gas. We have 3 different components. I'm going to obtain the number of moles for each component, and after that I will find the total number of moles that I have. Now, the number of moles for each gas can be obtained by dividing the mass of that particular component to the molar mass of that component. Okay, so here the lowercase m is mass of oxygen and uppercase M is the molar mass of oxygen. So this is coming from the problem, like right now in this problem, lowercase m02 is 2 kilogram, and this is coming from table A1, and the unit is kilogram per kilomole. So 2 kilogram divided by 32 kilogram per kilomole. Okay, so this molar mass comes from our tables. Table A1. So by saying A1, once again, I'm referring to this textbook, the Thermodynamics and Engineering Approach by Sengel and Bose. Okay, so this number of moles is going to be 0.0625 kilomole. Okay, and the unit of kilomole, basically this kilogram cancels this one, and then we have a kilogram in the denominator. So I do pretty much the same thing, the same calculation to obtain the number of moles, but for nitrogen this time. So that will be mass of nitrogen dividing by molar mass of nitrogen. So mass of nitrogen in this problem is 3 kilogram. I go to table A1 and read the molar mass of oxygen, and that is 28 kilogram per kilomole. Okay, so that gives me the number of moles of 0.107 kilomole for nitrogen gas. And finally, I do the same calculation for the propane gas. So the number of moles is equal to mass of propane. So this propane is subscript, basically. It should be M of propane to molar mass of propane. Okay, so mass of propane is given at 7 kilogram, and the molar mass for propane is 44.09 kilogram per kilomole. All of these molar masses, by the way, once again, are coming from A1. So we have 0.158 kilomole here. So by adding these three numbers, I can obtain the total number of moles that we have in this particular problem, or let's say in this tank. So N, or the number of moles of the mixture, is equal to the number of moles in oxygen plus the number of moles in nitrogen plus the number of moles in propane. Okay, and all of them are within my tank. So the number of moles in the mixture will be 0.328 kilomole. We have this much of moles within the tank. So I'm looking for mole fraction in part B. So mole fraction, we show that with Y. Mole fraction of oxygen is the number of moles in oxygen divided by the total number of moles we have in the system. And that will be this number, 0.0625 kilomole, divided by this number. This is the total number of moles that we have. Okay, that ratio is 0.19. So this is one of the answers in part B. This is the mole fraction for oxygen. Similarly, I do mole fraction for nitrogen, and that will be number of moles in nitrogen divided by the total number of moles we have within the system. So for nitrogen, we have this much of moles, let's say 0.107 kilomole. And the total number of moles that we have is 0.328 kilomole. And that gives a mole fraction of 0.326. This is another answer for part B. And finally, the mole fraction of propane is equal to the number of moles in this component to the total number of moles within the system. So we have, where is it? This much of moles for propane, which is 0.158 kilomole, and the total number of moles is this much, 0.328 kilomole. and that ratio will be 0.481. Okay, so all of these three numbers are dimensionless because they are kilomole divided by kilomole. But once again, if you add up these three numbers, this one and this one and this one, you will see that sum of them is equal to 1. So sigma yi is equal to 1, and y starting from 1 to 3. So these three numbers are answers to part B. And you will see that, if I get back to the problem statement, you will see that the mass fraction values are not necessarily the same as the mole fraction values, because in part A, we had 0.166 for oxygen, but the mole fraction was 0.19. So the numbers are not the same. Okay, so in part C, the question is asking for the average molar mass, okay? And in order to find average molar mass, or let's say the molar mass of the mixture, I'm using this correlation. I would say the molar mass of the mixture is equal to mass of mixture, lowercase is m, so mass of mixture divided by the total number of moles within the mixture. So lowercase is mixture, again lowercase m is mass. I know that the mass of mixture is 12 kilogram. This is what I found at the very beginning. So here the mass of mixture was obtained at 12 kilogram. So this is 12 kilogram here. And the number of moles in the mixture, I found it here. That is 0.328 kilomole. So capital MM, or the average molar mass, is 36.58 kilogram per kilomole. That means each 1 kilomole of this mixture has 36.58 kilogram of weight, let's say. Okay, and finally for part D, the question is asking for the gas constant of the mixture. So basically in this part, the question is asking for Rm, or R of M. In order to find the gas constant of the mixture, I'm using the equation Rm is equal to Ru, the universal gas constant, over mm. Okay, so this m is the molar mass of the mixture basically. Ru is the universal gas constant, 8.314 kilojoule per kilomole Kelvin. And I already found that in the previous part. In part C, I already have that. That is 36.58 kilogram per kilomole. So my Rm is going to be 0.227 kilojoule per kilogram Kelvin. So this is answer to part D, and this was the answer to part C.